All right, chemistry, Unit 4, Worksheet 3. We finished the notes yesterday talking about relative masses of atoms. So maybe all these atoms don't have the same mass. Let's see. Let's check this worksheet out. It says use the following information about the masses of elements in each pair of compounds to help you suggest formulas that account for these ratios. So we have in number one, we have these compounds, these two compounds that contain only carbon and oxygen. All right. And it says in compound A, we have 57.1 grams of oxygen per 42.9 grams of carbon. All right, so we're going to figure out that ratio for carbon, oxygen to carbon, and that's going to go here for A. All right. So can somebody take on the calculator? I just told you guys where that is on your phone. Uh, somebody take 57.1 and divide that by 42.9. Hey, Beyonce. 1.33. Thank you. All right. Now let's do compound B. All right. It's 72.7 divided by 27.3. 2.66. All right. How does the mass ratio, this thing that we figured out in number 4, how does that compare for compound B? How does that compare to compound A? Compound B is what? Thank you. Yeah, compound B is twice as large as compound A. Thank you. Okay, cool. All right, so letter C says express these ratios as improper fractions. So when we found this ratio 1.33, really what that's saying is 1.33 grams of oxygen per 1 gram of carbon. That's what we really found out. Okay? But now, to write an improper fraction, what we really want to try to get at here is if you remember when we're talking about the things combining in simple whole number ratios. Okay? Is this a whole number 1.33? No. So what we can try to do is maybe try to double it, see if that works. If we double 1.33, what would it be? 1.33 grams of O does in this relationship compares with 1 gram of carbon. Yep. Okay. So if I double it, I would get 2.66 over 2. Is that a good, nice, simple whole number ratio? No, it's not. What if we try to multiply both the top and the bottom by 3? What's 1.33 times 3? Sweet, I'll take it. If I multiply both those numbers by 3, it keeps the same ratio. Um, but what happens now is this 1.33 is going to become 3.99, and this is going to become 3. And what I like about this is, although it's still not exactly a whole number ratio, it's pretty close to being 4 to 3. Okay? So that's what I'm going to put down here for A. I'm going to write 4, and I'm just going to put 4O to 3C. Okay? Can you read that okay? 4O to 3C. Now let's try the compound B, see what happens. So obviously, if I start with 2.66 over 1, that's not going to work. All right. What if I multiply the top by 2? Do I get a whole number then? Or close to a whole number? 2.66 times 2, what is that? So that doesn't really sound like it works, huh? What if we multiply it by 3? 3, what is that? 7.98. So if I multiply both the top and the bottom by 3, I get 7.98 oxygen per 3C. So we'll use that, which is really going to be 8. We'll round that off to 8 to 3. All right, so we'll put that down here. 8O per 3C. So in the next part, letter D, it says for each hypothesis, sketch particle diagrams for the compounds of A and B that account for these mass ratios. You guys are just working with pens or pencils or whatever, so I'm just going to keep this simple in terms of the colors of the dots that I use. I'll just make either black dots or white dots. 4O over 3C, and then B is 8O over 3C. Yeah, it is. Because I'm so cool. All right. Yep. Pretty good ones. All right. So in hypothesis one, what I'm trying to show is those relationships in those improper fractions that we just had. Okay, so I'm going to write it to the side again here so I can remember just down here, not that you necessarily have to. But that first improper ratio was 4 O's for 3 C's, okay? So 4 O's per 3 C's. And then on the bottom we had 3 O's, wait, 8 O's, sorry. 8 O's per 3 C's. All right, so I'm going to do, in the first column here, hypothesis 1, if atoms of C and O have the same mass, how can we account for this difference in masses then? Any idea? So we know the mass ratio is 4 to 3, but if we're saying each atom of carbon and oxygen, they all have the same mass, how is there a difference in this compound? What would it look like? C and an O connected would be one of each, and then an O left over. Would that work? What if we just made it into like 7 total pieces, 4 O's and 3 C's? So maybe I'll do black dots for O, and this is going to be my compound. It doesn't really matter if it's accurate or not. I'm going to make 4 O's. These are all stuck together, by the way, even though there's a little space between them. So black is oxygen, okay? Maybe I should write oxygen because otherwise it looks like a white dot. And then just attach anywhere 3 white dots, doesn't matter where, something like that. And then I'll say that's going to be my carbon. So if each atom has the same mass, it would make sense that there's 4 masses of oxygen for every 3 masses of carbon. Does that make sense? So in this one down here, I'm going to do the same thing, but this time I'm going to make 8 O's. Uno, dos, tres, cuatro, 5, 6, 7, 8. And then I'm going to do 3 C's anywhere, doesn't matter, something like that. Okay, same legend. All right, so that would account for 8 parts oxygen in terms of mass, 3 parts carbon. All right, now what we can say in the second one is what if atoms of oxygen are heavier than carbon atoms by the ratio in compound A? Okay. What's that? Uh, Sorry. Okay, so if we go back to looking at the actual ratio, the actual number, and we just did one of each. Okay, so I just had like one oxygen and one carbon. Okay, and let me ask you this first of all: if we show one atom having more mass than another one, is there anything that we should change about it? Do you think when we draw it? Size of the particle sounds good to me. All right, so if I want to show oxygen having more mass, maybe I'll make it a little larger. For compound A, what was that ratio? And what was the first number we found up there when we took the 57.1 and divided by 42.9? 1.33. Okay, so if I do that, if I had a carbon, all right, here's my carbon. Should have did them the other way around. And I'll just say, in terms of relative mass, carbon has a mass of 1. If carbon's mass is 1, then that would mean oxygen would have to be 1.33. Okay? I'll make it a little bit bigger, and I'll say this is oxygen, and then I'll put a 1.33. All right? So if we had a bunch of those, it should work out that where we had that same 1.33 ratio in the mass. Okay? So we're using this as the numbers from the first part. Numbers from what letter was that? A? Okay? So numbers from A we'll use in this. Oh, it was a little a, wasn't it? And here we're using the ratios from C. Okay. Now in this next one, I would have to do, what was the number? 8 to 3. What is that? What 2.66? Okay. So I could do carbon, and then I would have to do an even larger oxygen. Okay, so it's still carbon with a mass of 1, and then oxygen, this time with a mass of 2.66. All right. Now, does that make sense, though? If we have, I mean, this is the same oxygen in both compounds. Does it make sense that in this first compound we would have oxygen with a mass of like 1.33, and then in the second one, all of a sudden oxygen has a mass of 2.66. So does that make sense? It does make sense? You think that atoms of elements can just change their mass to double? So there is another alternative here we can do. We could do, instead of doing one carbon and one oxygen, what we could do is one carbon with its mass of 1, and then break this oxygen up and say instead of one oxygen, how about there's two oxygens, about the size of this one up here, because each oxygen is going to have a mass of 1.33. Would this make more sense? It does, because now in both pictures, oxygen and carbon both have the same mass. Okay? So that would make more sense. I've got these two compounds. I know their relative mass numbers, what they've got here, these ratios, and I'm trying to figure out the formula. Okay? So what is the formula for compound A? How many C's do I have in compound A up here? 1. How many oxygens do I have? So how would I write that? C, what subscript do I put next to the C? Do I put, how many are there? How many carbons? Just 1. So do I write a 1? Okay. Okay, so remember when we do the subscripts and the little numbers to the bottom right, we write how many atoms are in that compound. But when there's just one, you don't write a number. Just going to be C. And then I'm going to stick right next to it, how many oxygen atoms do I have in this compound? Okay, now if there were two of them, I'd write two. If there were three, I'd write three. If there were four, I'd write four. But if there's one, the O itself just says there's at least one. No number next to it means there's exactly one. All right, so that's what the formula would be, is CO, carbon monoxide or carbon monoxide. All right, what about this one down here? What is this compound going to be? You got one C and two O's, so I'm going to put O with a little 2 next to it. We call that carbon dioxide. All right, so on the left-hand side, we're just going to say, well, if they had the same mass. And on the right side, hypothesis 2, which we really want to focus on because, as you've guessed, if you've ever seen a periodic table, atoms of different elements do have different masses. Um, we're going to try to figure out what it should be. What should that formula be by figuring this out? All right? And I'll let you guys work together, but make sure you're working. Okay? So let's get to it.